First day in Chapter 6, we're going to start using derivatives to do other things, to kind of apply, to help us figure some things out. And the first thing we're going to do with that is we're going to start looking at these things that we call slope fields. So one big goal for the day, sketching a slope field to represent a differential equation. Remember, differential equation is what was my y that I took the derivative of, or my f of x that I took the derivative of, in order to come up with a specific derivative or second derivative. And then we're going to try to sketch a solution curve, which we'll get to, that fits through a slope field. So their second goal is a solution curve idea. And third and final, we're going to see if we can work backwards. All right, which one of these might be the differential equation that fits the slope field that somebody put in front of us? So what's a slope field? So I've kind of written out what the technical definition is, or my definition is. Slope field just gives us a quick picture of what the tangent line would look like at specific points on a graph. So easiest way to kind of compare this, if we scroll down here and we look at this problem number 2, and we'll get to the actual question itself, but what you see right there, these little blue marks, are actually what the slope of the tangent line would be at each of those specific points. So if I was to take a dy dx and plug in the value at x equals 1 and y equals 2, that is a mini little picture of what the slope of the tangent line would be to this function at that point. So a slope field's purpose is to give us this quick little visual of what the slope of the tangent line looks like at many different values. So what we want to do then is we want to start by sketching the slope field for 1A. We want to make the slope field, which is not a hard thing to do. And then part B, we want to make the solution curve that fits through this differential equation. The solution curve is a graph. It's kind of like playing pinball. We're going to create this slope field, and then we're going to bounce the graph through there the way these tangent lines would force it to move. So here's what we have. So part 1A, sketch the slope field for x is starting at -3 and ending at 3, and for y starting at -3 and ending at 3. So you've got this graph over here on the right, and you've got this derivative that was given to you. I think I'm going to have to zoom this out a little bit. And what we're going to do is we're going to try to create this slope field. So we've got this derivative given to us, the rate of change of y with respect to x. We don't know what y is, but we could figure it out, and we'll talk about that in a little bit. But what we're going to do then is we're going to pick a random point. So let's say, for example, that I start out with the point -1, 2. Okay, the point -1, 2. So at the point -1, 2, we're going to plug those coordinates, those specific coordinates, into this derivative to find what the slope of the tangent line would be. So if I did that, well, it'd be 2 times the x value. So my slope would be -2. So the slope in this little circle right here would be for every 2 so we'd go down 2 for every 1 it goes over. So the slope of this tangent line at this particular value would be down 2 and over 1. Okay, well, let's say we took another point. Let's say we took the point -1, -2. And I did the same thing. So that would be 2 times -1 again, or -2. So this slope at the point -1, -2 would be exactly the same as the slope would be at the point -1, +2. Well, what I'm looking at is, it appears that the slope of this tangent line, the slope of the tangent line depends on x. So what is that going to mean? It means it doesn't matter what y value you put in, the x's are going to stay consistent. So what I'm going to know about that is, and whenever x is equal to -1, the slope of my tangent line is always going to be basically the same thing. And so if you look at this thing, what I have is every one of those slopes should be parallel. Those slopes should all be about -2. Okay, and is my drawing perfect? No, absolutely not. But we're trying to get an idea what this thing looks like. Okay, so let's say I pick another value. Let's say I pick x equals +1. So let's say I go to the point 1, 0. What's my slope? Well, my dy dx now would be 2 times 1, or 2. So when x equals 1, my slope is going to be 2. And they're all, again, going to be the same. That's the idea. So here my slope is 2. When x equals 0, I think my slope is going to be 0. When x equals 2, my slope is going to be 4. 2 times 2 would be 4, so this slope is going to be a little bit steeper. And when x is equal to 3, I think my slope is going to end up being 6. So steeper still. And I know that those aren't perfect, but we've got the idea. And then over here, when we start looking at my slopes, when x equals -2, my slope is going to be -4. And you can see how scientific I'm going to be, and then these would be -6 for my slope values. So what we've done is we've just created a slope field. And we've decided that the slope of the tangent line depends only on the x's, which means for consistent x values, we're going to have consistent slopes. When the x changes, it changes the slope. So that's part A. So we've created the slope field. Now part B, we're going to come up with this solution curve. Well, what's a solution curve? A possible graph of what the differential equation looks like. Well, what does this look like? Well, it appears to me like if I was to graph this function, I was going to draw a quick graph of what I have going on right here. It appears that my solution curves, these black equations, would be parabolas. If I wanted to put another one down here, it would look, again, same basic idea. It would kind of be bouncing its way through here. And you can kind of see that what I've drawn there is not perfect, but those are the idea of what I would have in terms of my solution curve. And if you wanted to prove this to yourself, if we knew that dy over dx was equal to 2x, well, what would you take the derivative of in order to get 2x? I think it would have something to do with an x squared plus a c, which makes sense because our solution curve would have to be some kind of a parabola. So there's how my pieces fit together as far as my slope fields. So let's come down here to number 2. So number 2, now we're trying to work backwards. Now we're looking at, all right, which one of these is the slope field? So the slope field, let's see. So if I look at these, it looks like the slope depends on y. Because for y equals 3, I have consistent slopes. For y equals 2, I have consistent slopes. So it looks like the slope depends on y. So if it depends on what the y is, that means it can't have an x in its equation. So I'm down to C, D, and E. The other thing I would notice is here we have horizontal tangents. We have horizontal tangents when y equals 0. Well, think about how we go about finding horizontal tangents. We take the derivative and we set it equal to 0. So which of these 3 choices that are left, where would they have horizontal tangents? Well, C would have a horizontal tangent at 0. D would have a horizontal tangent at 0. In other words, the slope would be equal to 0 when y is equal to 0. And E would have a horizontal tangent when y plus 1 would be equal to 0, or when y equals -1. So this one's out. So I'm down to either C or D. So your last choice, well, if I look at this, and the last thing I would look at is, I see positive slopes when I use positive y values. I see negative slopes when I use negative y values. Which one of C or D fits that description? Well, C is going to be, the slopes are going to be opposite whatever the y values are. D, the slopes would match the sign of whatever the y values are. So that's how a way we work our way through it. So your progression, see if you can find patterns for what the slopes depend on. Look for horizontal tangents, and then worst comes to worst, pick a point and plug it in and see what works. For example, to differentiate between C and D. All right, last problem of the day. Sketch a solution curve that has to pass through the point 2, 0, then solve the differential equation analytically. Analytically meaning see if you can work your way through it. So if I go to sketch this solution curve, if I started with my solution curve, I'm looking at these things, and I think my slope field doesn't appear to depend on x, nor does it depend on y. It's kind of all over the place. But I'm seeing, as I glance at it, I'm kind of seeing a circle. I'm seeing a point, and if it's got to go through that particular value, I'm thinking my slope field's going to look something like that. And no, that's nowhere close to drawn perfectly. But I need it to go through this point 2, 0 over here. That's my particular solution, but I think I'm looking at a circle. So I made a quick sketch. Now solve it, the differential equation analytically. The first thing I got to do is I got to separate my variables. So I'm going to multiply by y, dy over dx equals the opposite of x. I'm going to multiply by dx, so y dy is equal to the opposite of x dx. Now I'm going to integrate this thing. So if we go to integrate it, antiderivative of y with respect to y, well, that would be I think, a 1/2 y squared. And on the other side, antiderivative of x would be opposite of 1/2 x squared. And since we're probably looking to solve for y in a problem like this, I'm going to put in a single c, and I'm going to put it opposite the y that I'm probably ultimately going to solve for. So now we got a couple ways we could go. We could find c right now. If I wanted to find c right now, I'd use the point 2, 0. So if I know that, I'd put 0 in where I see a y, and I'd put 2 in where I see an x, and I would see what my value comes out to be. So if I do that, I think -2 plus c is equal to 0. So I think c equals 2. So what does this equation really look like? Well, this solution curve is really then 1/2 y squared is equal to -1/2 x squared plus that 2. Well, there's a solution curve. Now, if I wanted to play around with this equation a little bit, I think what we'd find is this would be a solution. You could have this as a solution, but what a lot of people will probably do is they'll go, well, you know what, I don't really understand what that equation looks like, so let's do a little quick algebra. Let's say we multiplied everything in that equation by 2. If we multiplied everything in that equation by 2, I'd have the equation y squared is equal to the opposite of x squared plus 4. And if I move the x squared over, I'd have the equation x squared plus y squared is equal to a 4, which is the equation for a circle with radius 2. So, and the center at the origin. So there's a lot of different ways that you could do this. A lot of people like that version the best. But that is an equation found both analytically and graphically for the solution to this particular slope field.